Welcome to the SOLIDWORKS Simposium, a place where we talk about all things simulation, where all simulation is treated equal. We don't discriminate. If we know it, we'll talk about it. My name is Enrique Garcia, the self-proclaimed simulation sensei and senior simulation specialist here at GoEngineer. I'm accompanied by the legend, the quantifier of quantitative results himself, senior simulation specialist, Nick Pusateri. How you doing, Nick?
Good. Happy to
Good
be
to
here.
see
How
you,
are
man.
you?
Well, doing good, man. Just happy to be back for the first episode here of 2025. So,
Yeah.
yeah, I can't believe this is show number 4 here, gentlemen. So, we have to thank GoEngineer for allowing us to continue our show, and also a big thank you to all of you customers and viewers who have attended throughout the episodes. We're just really happy to be able to continue to chat and collaborate with you all just on these shows. Yeah, also another first for us, Nick. This is our first show where we have a special guest. So we're joined today by our esteemed colleague, Bill Roos. He's our resident expert in simulation hardware recommendations here at GoEngineer. Welcome, Bill.
Yeah. Thanks, guys. Thanks for having me.
Yeah, excited to have you on today, and I can't wait to
That's
pick your
great.
brain. All right. So yeah, just a quick intro to the segment. So I think hardware recommendation requests for us as AEs I think any reseller, it's a request as old as time, right, fellas? I
Yep.
think I used to get this in tech support at least once a week, twice a week. Someone's building a new machine, and there's many ways to come up with a computer or hardware recommendation. And honestly, everyone's use case can be so different in our industries. So we're all designing very different products. So we want to go through with you how we come to a determination for hardware suggestions. So this is what we do here at GoEngineer. This method is broken down into 4 main categories. So I'll let you take it away there, Bill.
Sure. Yeah. CPU, RAM, hard drives, video card. Honestly, that's the order that I would put them in for importance for simulation. So, yeah, great lead in there. Let's boy, CPU recommendations. Man, you just want to jump right
Hey
in.
now.
Okay. Yeah. So as Enrique started saying, yeah, not only are your needs slightly different, well, the requirements for SolidWorks simulation or FEA is different than flow, is different than motion, is different than plastics, and that link there, the benchmark. That's one thing you can reference, and I will say if you're looking at synthetic benchmarks, that gives you a relative indication of CPU performance. It does not exactly tell you how well SolidWorks or SolidWorks simulation is going to run, but it gives you a general idea of how to compare or tier one processor versus another. So that's a
Might be
good
nice
thing to start
to
with.
look up your. Yes, sorry to interrupt. It might be nice to
Yeah.
maybe take a look at your machine currently and one that you're shopping
Mhm.
for to see. See if the. I keep saying this. It's my mantra, I guess. If the juice is worth the squeeze, right? You can jump up to the
Yeah,
next.
so yeah, I'll just mention this. So generally, when you're looking at benchmarks, you're going to see 2 different scores that matter. One is called a single thread rating. That is when one of your cores is working. You know, how good is it going to do? So single thread rating is one, and then they usually have a multi-core performance. That's closer to what we want to see. You know, we want to see all of our cores working. So with SolidWorks and with SolidWorks analysis products, you kind of need to know what both of those scores mean. So, all right, hey, let's jump into the next slide if you want.
Yeah, let's do it.
So I was hoping you toss me a softball here and cover motion first, but we'll get there. So SolidWorks simulation. Yeah, that knowledge base article is a really good thing to look at. Let's just say in general, because we have different study types and different solvers, there's not a one-size-fits-all CPU for SolidWorks simulation. Some of the solvers and study types are only going to be single-threaded, but several are actually let's break it down. FFE Plus and Sparse Solvers. FFE Plus is marginally multi-thread capable, where the Sparse Solvers are more multi-thread capable. But there's a limit to them, right, guys? I mean, we see this. You know, Nick and Enrique, I know you guys run into this. So let's just talk in general. The FFE Plus solver, it is or will thread out across 2 to 3 of your CPU cores for most simulation studies. So if you were to have a 16 or a 24 core CPU, you're not going to really see more than, well, let's see, a 16 core CPU, if you've only got 2 of them running, you're going to see what, 12 to 15% core usage. It doesn't sound that impressive, does it?
Not really.
Yeah. All right. So, but that's just kind of the thing that we get with the FFE Plus solver, the brute force solver. The sparse solvers are more multi-thread capable, which is a very good thing. But still, it's a desktop solver, so there's a practical limit. So in general, if you're going to buy a CPU for SolidWorks simulation, right now the sweet spot is somewhere, 8 to 12, even 16 cores. We're just not using more cores than that for study types and solvers with SolidWorks simulation. It's not high performance computing. It's not extremely scalable like some higher end FEA products are. So right now what we're looking for is as fast as possible, somewhere in the neighborhood of 8 to 16 cores for a processor. And beyond that, you just have more cores than the solver is going to currently use. And that's just, where we're at today with that. Yeah, so I'd actually recommend, go ahead and read that article. There's actually a PDF you can download when you go to that knowledge base article, and it gives you an indication of what parts of SolidWorks simulation are and are not multi-thread capable. The other thing is when you're looking for a CPU for simulation, hyper-threading on Intel processors, there's zero benefit there, so you can turn it off and there's zero performance hit there. In fact, sometimes hyper-threading, if it's on, can slow you down for an FEA problem.
Yeah, I remember doing that when I recently have a newer machine here, and I went to the BIOS, right, Bill, and then just turn off hyper-threading and be done with it.
Turn it off. Yep. And if you're using an AMD processor, it's SMT. They don't call it hyper-threading. It's synchronous multi-something or multitasking. It's essentially the same thing as Intel's hyper-threading. Zero benefit to hyper-threading. So, yeah, for SolidWorks simulation, you're looking at cores on your processor, not threads. Two very different things.
Interesting.
Yeah.
Well, let's take a look. I know we had
CPU.
that's CPU for simulation. Let's take a look at CPU for flow simulation. Bill, what can you tell us about that?
This is one thing that top blog that's listed. That was something that we did a lot of benchmarking for.
Sorry to interrupt you, Bill. We do have a question here from Charles here in the chat. He's asking if there's a difference in single core versus multi-core in a CPU.
For SolidWorks simulations purposes?
SolidWorks simulation, I'm assuming so.
That's what it fell under, yeah.
Yeah, so so single core, we generally don't get single core CPUs anymore. I mean, that's what we used to have years ago. If you're talking about
my Acer Aspire, right? That was
yeah, way back when. Yeah, 286 and 386 was single core processors. That's not the same. Although if you're asking, so like there used to be some server processors that would have basically 2 compute cores on the same die. That's a little bit different. As far as that goes, if that's what you're asking there, Charles, to SolidWorks simulation, it doesn't matter. It's just looking at total core count in your system. All right, back to flow simulation. We good there?
Let's go.
All right, so flow simulation. This is actually something where we've actually done quite a bit of benchmarking on it. The sweet spot for SolidWorks flow simulation is actually in the neighborhood of 20 to 24 cores. So flow simulation is more multi-thread capable than SolidWorks simulation up to a point. So yeah, when you're gonna do a flow simulation project, if you have a 8-core CPU, it's going to be decent, but 16 cores is going to be a little bit better. 20 to 24 cores is even better than that. But there's a limit. There's a practical limit to what the SolidWorks flow simulation solver is capable of. And some of this is actually a recommendation from the dev team at SolidWorks that the multi-threading capability of flow simulation kind of caps out somewhere between 20 and 24 cores. So yeah, you don't need any more cores than that. But it does scale up really well to 24 cores. But yeah, there's really no need to go beyond that for SolidWorks simulation products, or at least flow simulation.
And Bill, we actually have a follow-up question. This is related
Sure.
to number of cores from Charles as well. He has a new expensive CPU with 64 plus cores in it. He says, is there a benefit? And as you said, probably not. And this is
For
referring to his
solid, yep.
simulation product. So I think,
Zero benefit, unfortunately. So it has to do with how efficient a solver is at threading the processes out, and that means splitting out the job to populate those cores. And 64 cores for SolidWorks simulation, you're going to get zero benefit from that. In fact, I think what you'll end up finding is it's actually slower than trying to force simulation onto fewer cores, just because it's not as multi-thread capable. So,
and the
great
clocking speed
for
is
other.
typically slower,
Yeah,
right?
that's the other thing we run into. The CPU core counts that high are usually server-based processors, so lower clock speed. We want fewer cores and higher clock speed for simulation.
Great, thank you for that.
Yep. So next, I think we've covered flow.
Yeah, any questions on flow here? All right, let's move on here. Let's talk about motion, Bill.
Motion is easy. It is a single-threaded application. So here, honestly, the best thing you could do for a motion problem would be have a single-core, super fast, 6, 8, 10 gigahertz CPU if you could get that. Not practical today, but that's what motion does. It is unfortunate that it is a single-threaded application. It's always been a single-threaded application. Someday, maybe it will grow up and be multi-threaded, but today, SolidWorks Motion is a single-threaded application, so there you want as fast of a CPU clock speed as possible. So that one's pretty easy.
Yeah, it'll grow up to be a real boy at some point. The Pinocchio of our simulation tools.
Something like that, yes.
Wonderful.
Plastics, another one near and dear to my heart. Plastics solvers, similar to flow simulation, are very multi-thread capable. We're just starting to do some benchmarking on multi-core performance of plastics. So I don't have an upper limit that I can tell you, but I know in just some, testing personally without going through a full-blown, benchmark profile, plastics is multi-thread capable somewhere in the 16 to 24 core CPU range. How much bang for the buck you get beyond that, I really don't know. We haven't gotten that far yet, but one of our colleagues, Brian Pollock, does a lot of benchmarking, not only for SolidWorks, but also for SolidWorks analysis products. And he's starting to work on some benchmarks for SolidWorks plastics. But the solvers for plastics like flow are very multi-thread capable.
I have a question.
Sure.
Is there a particular brand of CPU that you prefer for, I guess, sim overall? Is for Intel versus AMD, or what's kind of your...
Absolutely, Nick. So for pure performance, personally, right now, I prefer AMD Threadripper CPUs. It's just
kind of
because
surprises me because like everything you see in marketing is like Intel.
Yeah. Listen, you can't go wrong with either of them. They both make great processors. But here's kind of the downside to the Intel CPUs right now. They split them up into what they call E cores, efficiency cores, and P cores, or performance cores. And sometimes the older you get with SolidWorks analysis products, they don't understand the difference between an E core and a P core. And when that happens, and hey, this was new for Intel, 3 or 4 years ago. What you'll find if you're using older versions of SolidWorks, that simulation will only run on the E cores, which are the slower cores on the Intel chips. Unfortunately, the solvers are getting better. They recognize these CPUs now, so you're running on most of them. But yeah, overall, I just prefer the AMD. AMD CPUs right now, especially in the Threadripper series, higher clock speeds generally than the Intel, and they're great performance. But you can't go wrong with either of them, honestly.
Okay, thank you.
Mm-hmm. Sure.
All right. Any other questions regarding CPU recommendations before we move on to the next segment? All right.
I don't see anything.
Yeah, I think we're good. Let's talk about RAM recommendations, Bill.
Oh, sure. So RAM, here's my general guideline. You should have 4 gigabytes of RAM per physical CPU core in your workstation. So if you had an 8-core processor, then you should have at least 32 gigabytes of RAM. 16-core processor, 64 gigabytes of RAM. That's just a good benchmark to have. Now, you don't want to have not enough RAM. Not enough RAM means that you're going to use other CPU components for storage. And then honestly, in the big scheme of things, RAM is cheap. So right now, I'd say at least 32 gigabytes of RAM if you're doing any kind of simulation is the minimum. Honestly, 64 is pretty much a sweet spot. Also, when it comes to RAM, buy the fastest RAM that your motherboard will support. And this kind of ties into the difference between CPUs and RAM. It's all about the speed. So your CPUs, they're generally measured in gigahertz today, unlike Enrique's megahertz Pentium way back in the day. That's billions of transactions per second. RAM is still measured in megahertz, which is millions of transactions per second. Your CPU in your system is not your bottleneck. The first bottleneck is your RAM. So get as fast a RAM as possible. That's going to help you out a little bit.
Yeah, I think
The other thing is
fastest RAM we have, Bill, is it DDR5 RAM at the time of this recording?
It is, but then they even go into different speeds of DDR5 RAM, which gets really convoluted. But yeah, so fastest RAM. The other thing to do is when you're buying a system, it'll say like dual channel or quad channel. You're actually more efficient to do smaller RAM modules, but fill up all the channels. So I know that may not make sense to many people, but let's just say you have a quad channel motherboard. You want to put in 4 sticks of RAM, populate all of the RAM slots on the motherboard. It's more efficient than a higher density RAM chip filling only one of your slots. So little advice there.
Interesting, yeah.
Yeah.
So that's the speed of RAM. What were you recommending for CPU speed? Because there was a question somebody asked, is what speed on CPU for simulation? What did you say back then?
Yeah, so CPUs, honestly, that really comes down to a budget question. In my opinion, buy the biggest, baddest CPU that you can reasonably afford and put in your system. Everything with simulation, just like SolidWorks, your CPU is king. So spend a little bit more money there. That's where you're really going to get the bang for the buck on performance.
Yeah, that's like your foundation for these hardware recommendations, right? It's the hardest thing to upgrade. You can upgrade them, but it's just it's the most expensive. I had a customer. He had like a Threadripper CPU. It was $10,000 on Amazon the other day. We're looking at it, and I think he had 93 cores on the thing. He's not going to be able to use all those cores, right? So
No, definitely not.
But definitely get the highest clock speed for the budget.
Absolutely.
Any other questions on RAM recommendations? We have a question from Imani. It says, is this being recorded? Yes, it's being recorded. So they're going to send this out, I think, tomorrow as a follow-up email. And also, we're recording this here as well, and we'll be putting it on our YouTube channel, I assume, here in the next couple of days to weeks. And so he wants to see if we have any a spec sheet, so he may discuss this with his tech and finance teams. So
a lot of doesn't our blogs cover a lot of that, guys? A lot of that.
So we did, Bill. I think you have one, no?
Yeah, the flow blog. The flow blog was about how many cores will flow simulation use, but there's not anything that's a specific spec sheet. That's that honestly, it comes down to what your company is budgeting for new workstations. That drives everything. How much money are you willing to spend? If you tell me you're going to spend $3,000, I'll tell you about what you can get. If you tell me you're going to spend $20,000, man, you can build a killer workstation.
Buy a new car too, right?
Yeah, that too.
We have another question here. Thomas from the chat says, is it only SOLIDWORKS that can't use more cores than 24? Is ANSYS capable of using more cores than 24, or is it general?
So I'm specifically talking about SolidWorks simulation capabilities and how many cores that either SolidWorks Simulation or SolidWorks Flow Simulation use. having used ANSYS quite a while ago, it can use more than 24 cores, but you're paying for per core usage. And then the follow-up question, 20K for a workstation? Yeah, that's actually overkill. A really high-end workstation right now for like SolidWorks Flow Simulation can easily run in the $10,000 to $12,000 range. But quite honestly, you could do really well with somewhere in the neighborhood of $4,000 to $5,000 for a desktop tower workstation today.
Great, thank you for that.
Mm-hmm. I think you got
right.
a couple more slides that we need to get through here, right?
Yeah, let's finish it off here. Let's move on and talk about storage solutions.
All right, so this one, neat little pictures there. So HDD, hard drives, platter drives, those were slow, mechanical drives. We don't use those anymore, thank goodness. SATA and mSATA, those were the, kind of the first foray for faster memory-based drives versus mechanical drives. M.2 is actually kind of the current standard that plugs directly into your motherboard. The eMMC, Enrique, I'm not sure where you got that picture. Do you know what eMMC is used in?
I don't recall. The person that gave it to me, hey, check this out. This is a cool
okay.
slide.
Well, that doesn't truly. So eMMC is actually kind of like the memory or the hard drive that's in generally your cell phone. It's not really something that we have in our computers and mobile workstations. It can be, but typically not. So here's my general recommendation. Windows, for whatever reason, decides it wants to write things at the most inopportune times. Especially when we're trying to run analysis. So the way we have our simulation workstations set up is most of our workstations, we have two M.2 SSDs. That's the current fastest type of drive that you can get. We have one of our drives set up for our boot drives and our analysis. Boot drives and programs. And then we have a separate drive that we put our projects and analysis work on. And what that does is it gives us the benefit of letting Windows do its thing on one hard drive, and we don't have to wait for Windows. If it decides it needs to write something in the background, we can continue on with our SolidWorks simulation work. And this is key. The SSDs that we're using today are super fast. And when we're doing analysis, there's a lot of data that's being written to your hard drive in the middle of the analysis. So you want really fast solid state drives that lots of data can be written to. These are almost on par with as fast RAM that you can put into your system, but they're not nearly as fast as your CPU. That your CPU is the fastest component in your system, hands down. But when it comes to storage, they rate them by class, like class 30, class 40, class 50. You want to get a higher class solid state drive and use those in your system. And again, what we do, one drive for our boot drive and programs and another drive for our analysis, gives you a lot of flexibility there. And yeah, that's kind of the best thing to do.
I didn't know that about class for drives 30, 40, and 50.
Yeah, it's just a naming. Honestly, what you're looking for is your your input output speeds, your read write speeds. The higher the better for simulation.
Also, that suggestion about two drives, one for your boot drive and one for your storage for analysis work and CAD models. You were also mentioning that at sometimes your Windows will just want to write to the hard drive all of a sudden, right? And if you're in the middle of a high-end calculation or analysis, then that could meddle if you're only using one drive, right? So
it can. Now, granted, on solid state drives, it's not nearly as important today as it used to be, but still, you don't want your simulation to slow down because Windows decided it needed to do something on your hard drive right in the middle of a big solve. So just my recommendation. Obviously, you don't have to do that, but it will make your life a little bit better. And honestly, just like fast RAM and fast CPUs, just look for the highest read-write speed that you can get.
Perfect. We got Ali here. He says he still has all the punch cards he used for his strength and materials course. So he wrote a program to calculate Moore's circle on there. That's great, man. Perfect.
You can tell he's young. He's very young.
He's a
Yeah.
young and spry gentleman there, Ellie. Thank you, Ellie, for that comment. Charles just says, what is the max memory bandwidth needed for flow, plastics, simulation, and motion?
As in maximum RAM usage? Honestly, that really, if I understand the question correctly, Charles, it really depends on the problem. Let me talk about SolidWorks simulation. We'll back up to that for just a minute. The amount of RAM you need depends on, honestly, the total degrees of freedom that you have for a finite element problem. And it also depends on the solver that you're using. So in general, the FFE Plus solver needs about 1 gigabyte of RAM per roughly 2 million degrees of freedom, whereas the Sparse Solver needs about 1 gigabyte of RAM per roughly 200,000 degrees of freedom. So let's say you had 128 gigabytes of RAM in your system, you would need a finite element problem somewhere in the neighborhood of, 60, 120 million degrees of freedom to populate all the RAM. That's beyond what SolidWorks simulation is going to solve. So you probably have more RAM in your system than you could reasonably populate for even a really big finite element problem, regardless of the solver that you're using. Hopefully that addresses your memory bandwidth question.
Right. Thank you for that, Bill. And also, we're at the top of the hour, ladies and gentlemen. Just want to let you know we have about 5 minutes or so of content left. If you need to leave, we thank you again for joining. We are recording this session, so it'll be available to you in case you need to miss the next segment there, or if you've missed a previous segment. But other than that, thank you for joining us today. We are going to continue our program here. We have about, again, 5 more minutes of content, and let's talk a little bit more. Any other questions before we move on? All right, let's talk about video. Or is there anything else that you want to add to a storage there, Bill, for us?
Nope. Nothing comes to mind, but yeah.
All right, man.
M.2 SSDs, high class.
Awesome. Let's talk
video
about,
cards.
Yeah.
Enrique and Nick, what do you guys prefer for video cards right now?
Oh, GeForce all the way.
Yeah. Love.
Oh yeah.
I can make
all right.
cases.
The one that renders the dragon, and like has the pretty pictures and explosions on it. That's the one I want.
Sure. All right. So when it comes to video cards, I am personally a fan of NVIDIA cards. I haven't used AMD video cards in quite a while, but AMD/ATI, they do make really good cards. When it comes to SolidWorks and SolidWorks simulation, you really want a professional grade or a workstation grade video card. Now, what do I mean by that? Well, that is with NVIDIA, that's your RTX graphics cards today. With AMD ATI, that's the Fire Pro. Versus the gaming cards, which are the GeForce and the Radeon cards. Now, it doesn't, people say, well, can I use a Radeon card? Can I use a GeForce card? Absolutely. They will work for SolidWorks, but they're not recommended. The difference is in the drivers that's being used in the background, the acceleration hardware. So your gaming cards, they are based on a DirectX architecture. What that means is they're really good for generating lots of triangles and flashy explosions and stuff like that for gaming. But the resolution that you're getting on that doesn't have to be accurate because they're really focused on, the speed of what's being displayed versus professional or workstation grade graphics cards. They're based on an OpenGL architecture. And there, what you're looking at is stable images. That's what we want for SolidWorks and for SolidWorks simulation. So get a workstation grade graphics card if you're going to work with SolidWorks. Again, the others will work, but at some point, this is what you might run into. You're starting to have graphics glitches. You reach out to GoEngineer's tech support. Maybe you submit a SolidWorks RX file and stuff. And if we have to submit that to SolidWorks, quite often the first thing they're going to say is you're using an unsupported graphics card. Let us know when you have a supported graphics card, and then we'll address your issue. So anyhow, just get an OpenGL, get a workstation grade graphics card, and save yourself some headaches down the line.
I used to do tech support. Just a real quick comment there, Bill.
Sure.
Years ago, and I would, when it comes to video card related issues in tech support with SolidWorks, I would have anywhere from no issues or running just a little slower to not even opening or crashing SolidWorks when you're trying to open the software. So it could be, it could really be a video card graphics issue. Or when I used to teach SolidWorks CAD back in the day, the question would come up. Video card recommendations and gamer cards versus CAD cards, and an easy experiment I would do for my students. If you guys have SolidWorks open right now, start a sketch and just draw a little line segment. You'll have the line segment and two endpoints. Now zoom into one of those endpoints with your cursor there, and eventually you're going to start to see that your endpoint on the line segment will disassociate or move or jump away from the line segment. And so that behavior will happen a lot sooner with a gamer card, because it's not built to render the geometry as accurately as it does for a CAD card. So you'll be able to zoom in a lot more into that line segment and endpoint, and without seeing that jump happen. Yeah, it's pretty neat. I used to like to show that. I do that exercise back in the day. It still holds true today.
I might have to use that now.
Yeah. All right, so video cards. Like I said, I haven't used AMD cards in quite a while. Nothing wrong with them. I'm just much more familiar with the NVIDIA cards today. Here's what we get asked quite frequently. Can I buy a really expensive video card and it will speed up my analysis? Well, today, none of SolidWorks, flow simulation or plastics or motion have GPU solve capability. So going out and spending, $8,000, $10,000, $15,000 on a video card does absolutely nothing for SolidWorks analysis products. So what you want to do is, a lot of times you'll see they tier video cards. They'll say entry level, mid-range, and so forth. Honestly, any mid-range graphics card is more than sufficient for SolidWorks simulation. Really, where the benefit of having a decent to higher end video card comes in is when we're doing our post-processing. So any type of animation, the fancy graphics output that we can generate from our simulation products, that's where your video card, and specifically the amount of video RAM, comes into play. But you don't need to go out and spend a whole lot of money on a video card. So right now, anything that's an RTX 1000, RTX 2000, those aren't the exact names of the video card, but that tier and higher is more than sufficient. You don't need to go out and buy the latest and greatest RTX 8000 graphics card. If you got money burning a hole in your pocket, downgrade your video card and upgrade your processor. So that's my recommendation there.
Perfect. Also, we have a link there, fellas. I get, whenever I get asked the question, go check out the video card certification website by SolidWorks. This is where all of the video card manufacturers report to Dassault Systems, and if it's on the list, then you have the green light to get it. So again, mid-grade video cards are the way to go.
It's an interesting comment. So the GeForce RTX 4060 Ti isn't the best. Well, for gaming, that's an awesome graphics card. But for SolidWorks, will it work? Absolutely. But that's a DirectX video card, not an OpenGL. So it's not the GeForce is the gaming side of NVIDIA, not the professional workstation. So sorry, Ross.
And there's another one that says, is 1 versus 2 make a difference for large models for post-processing?
So just in general for generating graphics, honestly, it's more about the amount of video RAM. I don't think there's any benefit to having 2 video cards for SolidWorks simulation. There is for other stuff related to SolidWorks when it comes to rendering, but not for SolidWorks simulation.